So finish off our integration by looking at an alternative way of doing integration by parts. What we got, you'll see I've drawn up a table. The first column's differentiation, second column's integration, and then I just have this plus minus in the third column. Now we know the integral of u to v, so we write it down. We're doing u to v because we want to differentiate the u, and the v will end up integrating. And so that becomes v, and then this is how we get our answer. Let me do it again slowly. Some people call it tic-tac-toe, because there's like three things you go tic-tac-toe. So the uv, we go down diagonally, but you go across, and that's giving me a plus sign. So it's plus uv. So that's why the uv is positive. But then we go down. Now, if I differentiate down in the first column, the second row becomes du dx, whatever we get when we differentiate u. If I integrate in the second column to go from v, I'll get whatever the integral of v is, dx. But then I go do that same pattern. This time it's minus I ended up with, so it becomes minus, and then we multiply those two together, and I get the integral of v du. And there's our formula. So that's the idea behind it. It's a different way of setting it up. So let's have a look. It's still the same ideas. You will choose, so differentiation makes it simpler to v, something we can integrate. That hasn't changed. Okay, so the first case we'll look at, where the two functions, one's a polynomial times something that can be integrated. So a fairly simple one here, we've got x cos x. So when we set up our columns, I'll differentiate the polynomial, and I'll keep doing it until I get to 0. So differentiate x, we get 1, differentiate 1, I get 0. Okay. Then I'll go in the other column, integrate. So working our way down, integrate cos, I get sine, integrate sine, I get minus cos. And so now I do that tic-tac-toe. So the first line I'm writing down, it'll be plus x times sine x, so x sine x. Then the next one I'll write down will be minus 1 times minus cos x, and so we get our answer, x sine x plus cos x, plus a constant. So it can be quite handy when you have to apply integration by parts more than once by putting it in this table. So if I had x squared e to the x, so I'll choose x squared for what I'm going to differentiate, and e to the x, what I'm going to integrate. So let's differentiate down the x squared column until I hit 0. So x squared goes to 2x, 2x goes to 2, 2 goes to 0. Then the integration column is going to be a bit boring, this one. I'm going to integrate e to the x, I'll get e to the x. Integrate e to the x, I'll get e to the x. Integrate e to the x, I'll get e to the x. Okay, so that's that one. So now, let's follow the pattern. So the first one will be plus x squared times e to the x. Next one, minus 2x e to the x, and then plus 2e to the x. And of course, plus a constant. So what happens when we've got a polynomial times something that can't be integrated? So now we're going to choose it to be our derivative. So we stop when the product of the line, we look across the line, that can be integrated. So integral of log x, set up our table. So I can't integrate log x, so it's going in my differentiation column, which means 1's going in my integration column. If I differentiate log x, I get 1 on x. Integrate 1, I get x. Now, the product of the line is 1. That's integratable. So therefore, it's x log x minus the integral of 1. Okay, x log x minus x. Let's try inverse tan. So this time, differentiate inverse tan. I'll get 1 on 1 plus x squared. Integrate 1. I get x, and x times 1 on 1 plus x squared, yes, that can be integrated, so I'll stop there. So I'll get x times the inverse tan of x minus x on 1 plus 1 on x squared. Now, this explains where I got the integral of 1 from. You might be looking at it going, where on earth did he get 1? But now that you can see what I've written down in this integral, can you see where I got the 1 from? Remember, we stopped when the line was integratable. So that's the integration that I'm writing down. 1 on x times x was 1. And this time, x times 1 plus x squared. But the sign I write down is the one in the next column, because I've already used the plus. I used the plus for the x log x, or in this one, the x inverse tan x. So I'll go minus the integral of the product of that row that I stopped at. And there, hang on, what is that? Oh, that's a log situation, isn't it? So I get minus a half log of 1 plus x squared. X cubed log x then. Well, log x, I'm going to have to use that for differentiation because I can't integrate that one. Differentiate log x, I've got 1 on x. Integrate x cubed, I've got a quarter x to the 4. Product of that can be integrated. Okay, so it'll be plus a quarter x, x to the 4 log x, minus the integral of the product. And the integral of the product there will be a quarter of x to the power 3. And so we integrate that, add 1 to the power over the power, we've got our answer. So if I choose to differentiate x cubed, so now it's the rule where I'm going to differentiate until I get to 0. So x cubed, 3x squared, so I get x log x minus x. But you see, I'm going to stop there rather than go to 0. Why? Well, look what happens. When I multiply that line together now, I've got 3x cubed log x. Hang on, that's the integral that I was starting with. And then I've got something easy to integrate. So rather than keep going with this one, I stop there. I can move the 3x cubed log x to the left-hand side, integrate the x cubed, divide by 4, and we get our answer. It's probably a good explanation as to why we don't choose the log x to be the integral. It's easier to go the other way. But theoretically, could do it that way. What happens if you've got two integratable functions? So you've got a choice. Well, we'll stop when the product of the line is integratable, so if you get to that situation, or it's a multiple of one of the other lines. So let's do e to the x cos x. I'm going to choose e to the x to be our differentiation, cos x to be our integration. First line, I end up with e to the x sine x. Stop when the product of the line is integratable. Well, that's not integratable. Multiple of another line? No, it's not. So we'll keep going. Next line. Okay, I've done my e to the x sine x first. Next line, e to the x minus cos x. That's a multiple of the first line. That's where I'll stop. So now we'll go minus e to the x times minus cos x, plus e to the x cos x, but then it'll be plus that last line that I stopped at. So the integral of e to the x cos x, which of course is what we started with. Move it to the other side, divide by 2, got my answer. Okay, some other examples then. Integral of x e to the power of x, and I don't think that dx is meant to be in the power. All right, so x e to the x, that'll become, we'll differentiate down to 0, integrate the other side, so we get plus x e to the x minus e to the x plus a constant. Inverse sine, okay. Differentiate inverse sine, I get 1 on the square root of 1 minus x squared. And integrate 1, we get x. That row can be integrated, can't it? Yes. So I can integrate that row, so that's where I'll stop. So we'll get plus x inverse sine x minus the integral of the row that I stopped at. So integral of x on root 1 minus x squared. I've got derivative on the function, so we end up with, it's just a du on root u, isn't it? So we get plus the square root of 1 minus x squared, plus a constant. Integral of the square root of 1 minus x squared over x squared. We can differentiate the square root of 1 minus x squared. We can integrate the 1 on x squared. That's probably the easiest way to go. So differentiate, I get minus x on the square root of 1 minus x squared. Integrate the 1 on x squared, I get minus 1 on x. So there's the first bit. I've now ended up with something that I can integrate because the x's will cancel, and I've got an inverse sine situation. So I'll go minus, 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 and we get dx on the square root of 1 minus x squared. So there's our answer, inverse sine. This last bit, taking advantage of Euler's formula. So bringing complex numbers into our integration. Reminder, e to the iota theta is cos theta plus I sine theta. Here's one from last year's HSC. Show that for any integer, e to the I n theta plus e to the minus I n theta is 2 cos n theta. Well, e to the I n theta, if I move it back to cos n theta plus I sine n theta, the second one becomes cos minus n theta plus I sine minus n theta, but we know cosine's an even function, so minus n theta will become just n theta on the cos, but it'll become minus sine n theta for the sine. That means the I sines cancel, and we're left with 2 cos n theta. Now a bit of binomial theorem. By expanding this expression out, show that this identity, cos to the power of 4 theta is equal to an eighth of, etc. Expanding it all out. There it is in all its glory. E to the 4a theta plus 4 e to the 3i theta times e to the minus I theta plus 6 e to the 2i theta e to the minus 2i theta plus 4 e to the I eta theta e to the minus 3i eta theta plus e to the minus 4i theta. I'm going to regroup them so that the coefficients in those powers are sort of the same, other than plus or minus, of course. That allows me to take advantage of what we just showed. So on the left-hand side, the first one becomes 2 cos theta. This e to the 4 iota theta becomes 2 cos 4 theta. The e to the 2 iota theta, etc. becomes 2 cos 2 theta, but times the 4 becomes 8. So then, expanding the left-hand side, I've got 16 lots of cos to the power of 4. Divide everything by 16, and we end up with an eighth of cos 4 theta plus 4 cos 2 theta plus 3. Hence or otherwise, find the integral of cos to the power of 4. Okay, so I now can substitute in my result, so it becomes the integral of, well, substituting in for the cos to the power of 4 that we just worked out, and now we've got some simple ones to do. Cos just goes to sine, we can sub the pi on 2 in, and we end up with 3 pi on 16 after all that substitution. E to the x cos x dx. Let's go back to that one. Here's another way of doing this. Well, e to the x cos x would be the real part of e to the x cos x plus I sine x. But e to the x times cos x I sine x is e to the ix. Now I can use my index laws and say, well, hang on, that's e to the power of 1 plus ix. Well, it's just an exponential. How do we differentiate, integrate exponentials? That'll be remember, it's all the real part of this. 1 over 1 plus I, e to the 1 plus ix. I just want the real part of that. Okay, well, the reciprocal of 1 plus I turns out to be 1 minus I, well, almost. It's a half of 1 minus I, so I'll bring the half out the front, because a half's a real number, so I can factorise that out of the real. And, well, now I'll turn that e to the 1 plus ix. Well, we know that that is actually up here, the e to the x cos x plus I sine x. So I've now turned it back into that. Now, e to the x, well, that's real, so I'm going to factorise that out of the real part. And I'm now left with 1 minus I times cos x plus I sine x. Well, I just want the real part when I expand all that out, and I get cos x plus sine x. Am I suggesting you do it that way? No. No, but it works. It's just another way of doing it.
Someone does it like that. What do you think he's marking that section?
All right. Look, I haven't sent any extra questions because I gave you heaps to do yesterday. But they're just some alternative ways of looking at the questions.